blinking. We're recording. All right, with absolute value inequalities, if we have greater than or equal to, we're going to write a disjunction with the word or. You say, what does that mean? What does that mean? If you graph two inequalities with the word or, I'm trying to see how much you guys remember. You just put them both on the number line, and usually a disjunction graphs with two rays going in opposite directions on a number line. But when they come at each other and they cross each other, it is possible to have what? Anybody know? This line coming this way, this kind of line coming this way, and they overlap, they color in the whole number line, and so the solution is, again, like he said before, all real numbers. Okay, it's possible with a disjunction. If you have a less than or equal to symbol, it's an and sentence, which means you're graphing a conjunction. What does that mean? All right, with a conjunction, whereas this was a union, this is an intersection. With the disjunction, I told you, let me go back for just a second. With the disjunction, I just told you, hey, let's put them both on the number line. When I think about a union, I think about two people getting married becoming one. My two graphs going to get married become one graph. Whatever happens on the number line, if they're opposite rays, if they're crossing each other. But with a and sentence, with a conjunction, I'm looking for points of intersection. All right, you guys drive. What's an intersection? Where does Highway 71 cross Highway 35? Do you know? You come across it unless you came Dutton, right? It's where the two roads meet, the points that they have in common. So that's what we're looking for with an intersection when we graph two inequalities. When we're looking for an intersection, those graphs will more than likely, most of the time, come at each other, and wherever they cross each other, wherever there are points in common, and you'll see more when I do a graph like that, wherever you see points in common, those are the solutions. And normally, an intersection, a conjunction graph just looks like a little bitty line segment. But what if? What if it goes the other way? What if instead of meeting each other on the graph, one goes to the right, one goes to the left, then they would have no points of intersection at all. So what's my solution? If there are none, no solution. You guys are looking at me with blank stare, so I need to back up a little bit, okay, and just work some conjunction and disjunction problems. All right, let's say, for example, that I have 2x minus 3 equals 6, and, no, not equals, I'm sorry, I need inequality right here. Greater than. I better make it simple. I better not have any fractions involved. Hang on just one second. There we go. Now over here, okay. Now I see the word and you say, well, it's just part of it. I'll skip that. I might not even write that down. You better, because that's telling you what to graph. This is telling you I'm now looking for points of intersection. Now, if you'll notice, I've backed way up, and I haven't even done any absolute value anything yet. We're taking a step back into Algebra 1 right now, okay? So if I add 3 to both sides, and I divide by 2, I get this. Over here, if I add 1, I'm looking for a number that is greater than 5 and at the same time less than or equal to 16. Better make my number line big. Okay. Now, when we were in Algebra 1, I taught you to graph above and below the number line to see where the color. Remember, we got 2 different colors of colored pencil, and we'd say, where's their purple and blue or whatever. Okay, so greater than 5. Why did I do an open circle?
Doesn't have the equal to it.
Because it doesn't have an equal to. It's not including the 5. So greater than 5 is going this way. Okay, then we get another color. Pick green. And then less than or equal to 16. I'm going to color in that because, like you said, it's or equal to. And then less than's going this way to negative infinity. All right, where is there purple and green? Well, 5 is not included there, but it's included here. So I'm going to put an open circle there. 16 is included here, and it's included there. I'm going to put a colored in circle. And everything in between is both purple and green, and so we colored it in. Those are the points of intersection. Now, purple keeps going that way to infinity, and green keeps going to the left to negative infinity. But there are not both colors there. There are not both graphs there. I'm just looking for the points of intersection. And normally, a conjunction, an and sentence, looks like a line segment on the graph. That's what that one looks like. Ring a bell? With set builder notation, I read a graph like I read a book from left to right. And I say, okay, where did this start? It started at 5. All my solutions are between 5 and 16. And by the way, 16 is included, so I'm going to do a colored in or equal to right there. I had it colored in circle, so I'm going to do an or less than or equal to right there. Now that's set builder. That's saying all my solutions are sandwiched in between this number and this number. I have my smallest number, my largest number, just like on my number line, reading from left to right, okay? Now why have I got less than here? Open circle there on this graph. And then why have I got an or equal to there? Because it's colored in there. All right, now let's look at interval notation. To me, interval notation is even easier, okay? Now remember, interval notation, I'm putting where I start and where I stop. This is an open circle. And if you remember the day before yesterday, we said an open circle is parentheses. I am starting at 5, but I'm not including 5. And then I'm going to 16, and hey, I'm going to include that, so I've got a bracket. That's what interval notation means. When you look at that, hopefully you're on the ACT, or you're somewhere, you're looking to, what's this solution mean? This solution means that the solutions are all between 5 and 16. It's not an ordered pair, even though it looks like one. All the solutions are between 5 and 16, and that bracket tells me it also includes 16. Are we lost? Good so far? Maybe we better do some more before we get into absolute value. Alright, when we change words, change or, that tells you that when you start to graph, you're going to be looking for points of intersection. So if I divide both sides here by a -2, x is less than -8. Why did I flip that? It's an inequality.
You divide by a negative.
I divided by a negative. Lots to remember. I divided by a negative, so I flip my symbol. If you don't know that, make your little note right there. You flip my symbol, divided by negative. All right, same thing's going to happen on this problem too. It's going to become greater than And all that stuff we talked about the other day. But let's talk about the graphing now. Okay, so with or, remember it's just like they get married. It's a union. Just putting whatever together, okay, on the same number line. So less than -8 greater than or equal to -6. Set builder's pretty easy. Just basically look at what the number line says and what this says. That x is less than -8 or x is greater than or equal to -6. The reason I can't do it as a sandwich, you know, the smallest number, the largest number, is because now my solutions are not between two numbers. It's not a line segment anymore. I'm not saying the solution is between -8 and -6. Actually, those are the only things that are not solutions, right? On my number line. All right, now here comes interval notation, and this is interesting. Remember, we read graph like we read a book, so let's read it. Where does this graph start? Where's this going? It's going to -infinity. It takes a stop here at -8, which, by the way, is open. I wrote the wrong thing on you guys. I said union and wrote intersection. Sorry. Forgive me. Alright, so this is a union, and this is the symbol, mathematical symbol for union. It looks like a U without the stick, right? The symbol for union. Alright, and then the solution picks up again at -6. And where does it go? Positive infinity, and infinity is always open. Now that's just a simple, and I use that word loosely, that's just a simple inequality. But I can tell by looking at some faces it's been a while and we don't remember stuff. You remember some? Is this problem, let's see if you guys get it right because I missed it a minute ago. This and sentence, is it a conjunction or a disjunction with an and? Conjunction. Is it an intersection or a union? Intersection. Okay, now let me tell you this. When these are the same, more than likely the book would write this problem like that. More than likely, when these are the same, the book would give you that problem like this. So wait a minute. Now, this symbol right here turned around. Did it? I mean, forgive me for my elementary speech here, but the mouth is still open toward that, isn't it? Right? That's what my elementary teacher said. The mouth's open toward the bigger number, and it still is. It's just that when I flip these around, I also flip my inequality symbol around. All right, now we look at this problem as having 3 sides. Here they are. 1, 2, 3. My objective is still to solve for what? X. I get X by itself. All right, so what is in the way of X being by itself, an added 15 and a multiplied 2? What do you think we would get rid of first?
The 15.
The 15. Okay. So I've got 3 sides. I'm going to subtract 15 here, and here, and here. You guys are doing it in your head. Now you've got 3 sides, okay? Be careful. All right, so -3 and -15 is -18. I still don't have X by itself. I've got to get rid of a multiplied 2. So I divide by 2. This conjunction this and sentence I made into, and this is probably not mathematically a good word, but I call these sandwiches because I've got my variable sandwiched in between two values, and when I get my answer, it still is. Now to me, that's really easy to graph because what that's saying is that all my solutions are between what two numbers? -9 and +3. So if I'm looking at my number line, now, a couple ways to look at this. You can do it like we did that problem before this. Say, okay, I'm going to do above and below. I'm going to say, x is greater than or equal to -9. Okay, well, I'm going to color that circle in and go this way. You can say, okay, well, when I read it over here, it says x is less than 3. Okay, that's an open circle going this way. And the way I did this same type problem a few minutes ago, I'm going to say, okay, where is there now red and green? Between here and here. But wouldn't it have been so much easier in this kind of problem when it's already a sandwich to go, okay, well, all my solutions are sandwiched between here and here. To me, that's easy to read. Where are they? Oh, between here and here. So they're on the number line also. When they write it instead of an and sentence as a sandwich, it also makes it easier, much easier, to do set builder notation. Where's my solutions? My solutions are sandwiched in between -9 and 3. That's where they are. And then interval notation, my solutions are sandwiched in between -9 and 3. So even though, I think that's easier to work than an and sentence because it keeps it all together, all as a sandwich, and you know that's what your graph is probably going to look like anyway. So that was a whole lot to take in. Does anybody have a question? Come on. Y'all are looking at me like. Is it easy?
Yes.
Let's do a little practicing on page 59. 53 to 71 odd. And let me just walk around and help and answer any questions you may have, because we have to do this before we do any absolute value inequality.